Good afternoon, good evening, everyone. Today I will talk to you about a totally different topic, which is about security. And we've talked a lot about automation, and I will talk to you about a project we've been working on, which is Vespa, to go towards a fully automated cloud security. So this is the result of a collaboration between Orange and Telecom Sud Paris, and it was work also performed within the OpenCloudWare project. So a bit of motivation, as you probably know all, due to sheer complexity, security has become a #1 adoption stopper to cloud computing. You know all the bright side of the cloud computing, but this is the dark side. And this complexity leaves the door open to many types of threats. So coming from the inside, legitimate users, overprivileged admins, or from the outsides, and here you have a number of them. And when you look on the side of the defense, and you have a great heterogeneity, both on vertically in the different layers or horizontally between the network and the system. So to master mushrooming heterogeneity and vulnerability, self-protection has been advocated as a promising next step to fight this situation. And with the promise of a simpler, stronger, more efficient and more flexible protection through automation of security with well-known benefits such as lighter administration, lower incident response time or reduced error rates. And so this gives rise to the concept of self-protecting or self-defending clouds, depending on the terminology. However, there remains one but, and that's one big but, is how do you design self-protecting clouds? So to achieve that goal, you must be faced with three major challenges. Challenge #1 is multi-layering. So to put it simply, the infrastructure of the cloud is built from a number of different layers, and each layer has its own security mechanisms. However, these security mechanisms generally do not talk to one another. However, the attacker will try to attack the infrastructure using several layers at once. So some things must be done there. Challenge #2 is multilaterality. So here, the fact is that the cloud includes multiple stakeholders which have their own security objectives, their own policies, and thus it requires different monitoring granularity to try to reconcile those different policies. And #3 is openness. We're not in a closed system. The topology of the different stakeholders is dynamic. You have new threats which may arise into the system, which may be unknown. And so here, chief concerns may be interoperability with third-party security components, and so you must have an open architecture. So to face these concerns, to build self-protecting clouds, you must face and you must cook your cloud using 4 major principles. Principle #1 is policy-based self-protection. That is to say, the architecture should be a refinement of a well-defined adaptation model based on policies, which brings well-known benefits in terms of adaptability. Principle #2 is cross-layer defense. That is to say, the security mechanisms should not be placed only in one layer only in terms of detection or reaction, but they should be synchronized between the different layers in order to get the overall picture of an attack. Principle #3, multiple self-protection loops. You must have different levels of granularity to manage security. So you must have different loops to automate and regulate security that must be defined and coordinated. And finally, principle #4, open architecture, you must have in your infrastructure different detection and reaction strategies and mechanisms to be able to face unknown threats and to be able to include new security off-the-shelf component in the architecture. So these are principles. Now come to reality. So what is VESPA? So VESPA stands for Virtual Environment for Self-Protecting Architecture. So it's an autonomic security framework for regulating protection of IaaS resources based on the previous principles. So its aim is to regulate security automatically based on the previous principles with a cross-layer approach, multiple levels of supervision granularity, and an open and flexible architecture. Vespa is also a framework with an implementation over KVM, and a typical application can be used for risk-aware quarantine of VMs. So the idea here is above your infrastructure, IaaS, you superpose autonomic management plane with detection, decision, and reaction steps. Typically, an intrusion detection systems that will collect security-relevant events, that will feed these events to a decision center, which will be able to take the security decision, then to transmit orders to the firewall in order to dynamically, according to the risk level, control inter-VM communications. So, in more detail, how does Vespa work? So, the Vespa system architecture is a layer-oriented architecture organized into a number of planes. So here you have a picture of a IaaS infrastructure with a number of planes which are represented vertically. So layer 1 may be the VM layer, layer 2 may be the hypervisor layer N may be the physical layer. And you have 4 planes. At the bottom, you have the resource plane, which are the resources you want to protect. Above, you have the security plane, which contains a number of detection and reaction components which may act on the behavior and state of these resources. So think of them as intrusion detection system or firewalls. At the top, you have the orchestration plane, which contains the decision-making logic to manage security both within a layer and a cross-layer. And between the security plane and the agent plane and the orchestration plane, you have a mediation layer built from a number of agents. So you have 2 hierarchies of agents, one hierarchy for detection to aggregate events coming from the security components to the decision layer. And when you get the order from the decision layer, a reaction hierarchy of agents to propagate that decision down to the security components. So then you have a satisfaction of the VESPA principles. Basically, the framework is policy-based, which allows you to manage security with a well-defined self-protection model. Protection is automated at 2 levels, both within and across IaaS layers. These different self-protection loops may be flexibly orchestrated, which allows to put in place a rich defense strategy. And finally, this architecture is layered, extensible, in order to be able to introduce in the architecture easily off-the-shelf security components. So I will not bother you with the details of the security model, since you have, as traditionally, assets, threats, managers to protect them, and the framework is policy-oriented. Just to give you a flavor of how it works, I will just show you how the agent plane is built. So in the bottom, you have agents, you have security components, which are typically intrusion detection systems or firewalls. And at the top, you have the decision-making logic using orchestrators. And then you perform the loop as follows. You sense the security context from the security components. You aggregate this context in order to get the overall picture of your security context, going up through the hierarchy of detection agents. You take a decision to reconfigure or not the security policies in the horizontal orchestrator, and then you push that decision down to the security component. Into more detail, this figure shows you how to implement risk-aware quarantine management. So without going into the detail, what you can see is that you have the different planes in the different colors, and what should be able to, the main points to remember here is that you have three main loops in the infrastructure. You can have a feedback loop, a feedback security loop, just at the VM level. Basically, you detect a virus in your virtual machine and you are able to clean that virus within the virtual machine. That's the first loop. Second loop, you want to go a bit further. You want to cut the communication. And for this, you're going to interact with the hypervisor. And so you're going to go up into the cross-layer orchestrator and go back down to give orders to the libvirt firewall. Or third loop, you may also give orders to migrate the virtual machines to a secure quarantine zone, and so the reaction mechanisms may be also the migration manager to migrate the virtual machines from the production environment to the quarantine zone and back. So in conclusions, some key points are written here to keep in mind about Vespa. So Vespa is an architecture for effective and flexible self-protection of IaaS resources. Basically, you have two-level tuning of security policies, coordination of multiple loops, and an open design in order to be able to integrate off-the-shelf security components. So ongoing work. Actually, Vespa is about 8,000 lines of Python code running over KVM. We're currently implementing a C version using Fractal, using a number of security services which are aimed, such as intrusion detection, antivirus, log analysis, and firewall and mandatory access control. Ongoing work is to extend Vespa to the multi-cloud setting, to have inter-cloud security using a security domain. If you want to know more, I invite you to read our paper, which was recently published on the International Conference on Autonomic Computing by IBM, which appeared in September in San Francisco. And this concludes my presentation, and I'll be around to take questions if you have more information. Thanks a lot.